Hey everyone, trying something different today, a video instead of a long written generated post. I have been working on a Go project that solves a real problem. I keep running into, basically parsing tightly packed UDP packets at bit level. Let me walk you through the problem first, what I found when I looked for solutions and what I ended up building. In real-time systems, normally UDP sends an event as a separate packet. As you can see, event A, B, and C. Each of them gets their own header, their own syscall, basically three times the overhead. A tightly packed UDP takes a different approach. It batches everything into a single packet per request. Same data, one header, one call, roughly one third of the network overhead. This matters the most in real-time systems like competitive gaming, VPN tunnels, IoT sensors, and even financial data feeds. Anywhere latency and bandwidth are critical. Here's an example of what I was working on while building an app in Go. Within a single 50 millisecond game tag, the engine writes player position, action events, and a heartbeat into a shared byte buffer, packing every field at bit level to squeeze out every unnecessary byte. So basically, one send call, one UDP header, and 54 bytes total. This kind of bit level packing introduced a problem. The server now had to unpack and validate every field manually using raw bit arithmetic. Missing one field could lead to silent corruption. In my case, I was checking if the position is under the range of 500, 200 coordinates, or even if the ammo is greater than the length 0. Adding a new field to the protocol, every parser that touches those bytes needs to be updated by hand or through a programmatic logical operator. Get one offset wrong, the client, or in this case me, received garbage data. And the application breaks in many ways that are impossible to trace. I had this case or this exact issue in three places in the last 3 months, playing Path of Exile 2, where the player stat desynced mid-combat. Secondly, a Go-based VPN app that I was using where the session dropped silently under the load. And of course, the Go application that I was building myself, the same class of bug, different context. Same root cause every time, manual bit parsing with no safety net. The best example of this problem being solved is in Python. Python's construct library has existed since 2002. You can define your packet schema declaratively, field name, type, bit width in plain readable code. No bit shifting, no manual masking. You can use nested structures, enums, conditional field, and validation all work out of the box. I think this is a gold standard for this problem, to be solved. On the other hand, Go has nothing like it, and that was a deliberate decision because based on this formal proposal that I saw on GitHub for requesting native bit and byte allocation in structs, the Go's core team position is very clear. This belongs in a library and not in a language. So that's why I made an attempt in trying to build this particular library. Why I was motivated to work on this was the other third party alternatives lacked in the following. The first one, Marshall was not even implemented. And in the second one, it required nested word structures. And in the third one, it was more of a forensic tool driven by JSON profiles, definitely not for production network code. Furthermore, none of them had validation or explanation or difference, and all the projects effectively got abandoned. So I ended up building this library called Nibble in Go. The idea is simple, similar to Python's construct, which lets you describe a binary protocol in plain readable code. The library does all the bit math for you. Nibble brings in the same philosophy to Go, using something Go developers are already familiar with, structure tags. You define your packet schema once as a structure. Every field gets a bit stack telling Nibble exactly how wide the field is on the wire. Take this game packet as an example. Is alive is basically one bit, so it can be true or false. We have weapon ID, which was 4 bits. In my case, I was supporting 16 weapon types. And health was a 9 bits because a player's health can vary from 0 to 511. 9 bits on the wire, but stored as a unit of 16 in our Go code, because 511 does not fit in a unit of 8. So Nibble bridges this gap automatically. The entire packet fits exactly into 8 bytes, 64 bits in total. In my case, I was sending 60 times per second per player. This single structure definition is everything Nibble needs. The bit layout, the validation ranges, or the Marshall and unmarshal logic all derived from this tag alone. To define what Marshall or an unmarshal is, JSON.marshal turns your structure into JSON string. JSON.unmarshal turns into JSON string back into structure. Nibble does the same thing, but instead of a JSON text, it works with raw binary bytes packed at the bit level. The three main functions we have is validate, explain, and difference. Validate, Nibble knows the maximum value for every field from the bit width, and explain basically converts your raw hex bytes into plain English, saves a lot of time when you're debugging. Difference compares two packets field by field, invaluable when you're trying to understand what changed between two captures. And when your protocol evolves, say the health expands from 8 bits to 9 bits, you change one structure tag. Nibble recalculates everything: the bit math, the validation range, the marshal, the unmarshal logic, and updated automatically. No more hunting through manual bit shift code, hoping you caught every place that needs updating. The truncated packet arriving from the network, Nibble returns a typed error and not a panic error which might bring down the server. If been a field overflow from a malicious client, we catch it at the library level before even it reaches the application logic. Let me show you the benchmarks. Three numbers tell the story: 10 times faster than the other alternative, which is go bitfield, 5 million packets per second, and 182 nanoseconds per packet to unmarshal. Initially, Nibble was not always this fast. The version 1 hit about 2000 nanoseconds per packet for both marshal and unmarshal. And the fix was schema caching. Instead of using reflection on every single call, Nibble now parses the structure tags once, caches the full field layout in memory, and reuses it on every subsequent calls. And here you can see the green bar being 182 nanoseconds unmarshal and 155 nanoseconds to marshal, which was a 11x improvement from one optimization. Here's another detailed comparison of the parsing speed between Nibble versus manual and Goldfield. Against manual bit manipulation, yes, manual wins on raw speed. I'm not hiding the number. Manual bit math happens at the CPU level, which is always faster. Against the Go bit field, only other Go library with unmarshal support, Nibble is consistently 10 times faster across every data size. 1825 nanoseconds versus 182, and GoBit field never implemented Marshall. This part of the chart shows real workloads from a small IoT hub to a heavy game server. The amber line is a Nibble's capacity, 5.5 million packets per second. Everything below that line, IoT, small game server, medium game server, heavy game servers, Nibble handles all of it comfortably. Only extreme frequency, trading pushes fast Nibble's capacity at 100,000 packets per second. A realistic production game server, Nibble only uses 2% for one core CPU. One honest thing worth mentioning is Nibble currently allocates twice per operation in terms of memory allocation. Those two allocations add GC pressure at scale. Eliminating them is our next optimization target. Let's look at the safety comparison table. And this is where the real argument lives. Speed is one dimension, safety is another. In the first scenario, where we have truncated packet input, Nibble returns a typed error. A manual code might lead to a crash or a panic state. In the second scenario, we have field overflow. Nibble catches it, whereas a manual code might silently corrupt your data. Let's say there's been a change in the protocol. Nibble needs one structure tag to be updated, whereas in the manual code, we need to refactor across every place that touches those bytes. You're not choosing between Nibble and speed. You're choosing between Nibble and the total cost of doing this manually, writing it, testing it, maintaining it, and fixing it every time when your protocol changes. The overhead is real. The safety guarantee is even more real. That was Nibble, everyone. I built it to solve a problem I kept hitting in my own work, and I suspect I'm not alone. If you work with binary protocols, game servers, VPN tooling, IoT backends, network security, or anything that deals with tightly packed UDP or custom binary formats, I would genuinely love to hear your use case. Does this solve something you've been doing manually? Is there a protocol that you wish Nibble already had a schema for? Is there a feature missing that would make this useful for your specific problem? Drop it in the comments or open an issue in GitHub, or feel free to text me on LinkedIn, or maybe just star the repo if you think this fills a gap. Link is in the description. Thank you for watching. Have a good day.